Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our, one of two webinars that we'll be having in March. This one is DAS, DTS, DSS, a perfect toolbox for well monitoring. And we're very privileged to have one of the co-founders of FEBUS Optics, which is a relatively new member to FOSA, and we welcome you. And we're pleased to have as our presenter Vincent Lantic, who is one of the co-founders of FEBUS. So Vincent, we look very much forward to hearing what you have to say.
Yes, thank you, Mark, and thank you to the association for giving me the opportunity to present this presentation, which is entitled DAS, DTS, and DSS, a perfect toolbox for rail monitoring. So first, as a co-founder of FEBUS Optics, I will present you briefly FEBUS company. So FEBUS is a French manufacturer of innovative distributed optical fire sensing solutions. We are based in France, mainly in Pau, in the southwest of France, for our headquarters. We have also this nice test facility you can see here in the bottom right of the slide, which is in Pau as well. We have some geophysicists in Strasbourg, in the northeast of France, and we are present commercially in Paris and worldwide in Houston, Texas, in Tunisia, and in Abu Dhabi, Middle East, Emirates, sorry. We are providing state-of-the-art monitoring solutions through our patented technology. All the technologies I will present today are patented. We are giving a strong R&D effort to increase our product portfolio. And we are as well focusing a lot on quality through the ISO 9001 standard. And we are certified to it. So what do we do? As I said, we are specialized in distributed optical fiber sensing. So our mission is to deliver a high performance and cost-effective fiber sensing solutions. For customers, they have to be cost-effective, but robust, easy to install and use. So we are addressing several markets, from oil and gas and geothermics through perimeter security, geophysics, and more particularly seismic acquisition, civil engineering, or cable monitoring, and marine renewable energy, and railways and roads. So, as I said before, we have a nice facility, which is our test center here in Pau. So it's nearly 500 square meter building on the top of 2,500 square meter field. And then in this facility, so you can see a picture of the inner part of the facility, we can reproduce field conditions under a controlled environment. So we can reproduce this condition for several experiments, simulating several applications. First is pipeline integrity. I will develop more on the following slide. Cable or cable metering, tension or electrical tests. Third part, perimeter intrusion, because our fence on the field is equipped with fiber optics. We can produce ground movement here in the trench to simulate landslides, and more on demand, we can perform on-custom test or on-custom demonstration on requirements from any customer. So here, a focus on the pipeline application. So you have seen there is a long trench, 28-meter long trench in the middle of the building, and we can fill this concrete pit with soil, and into this soil, so we can put a pipe, and this pipe can be pressurized with water or gas, water at 20 bars and gas at 50 bars, and we can equip it, of course, with fiber optics, and then produce controlled leaks with controlled flow. To move everything, we have this 5 tons overhead crane, and then, of course, we apply our technology on those fiber optics, equipping the pit in order to detect leaks or soil movement or third-party interference, as with a truck, for example. So our technologies. So our technology is, of course, distributed optical fiber sensing. How does it work? So all the intelligence, all the technology is here in this box. So that's what we patented. That's what we are selling here, this box. So you plug an optical fiber cable to this box, and a laser pulse in red here will be launched into an optical fiber inside an optical fiber cable. And when this light pulse is propagating along this optical fiber, a part of the light is backscattered. This means it's propagating backwards. So all along this pulse, all along the fiber is losing energy and giving energy to this backscattering light. So since we know perfectly the speed of light inside this optical fiber, we know that when the energy comes back to the equipment at a given time, it corresponds to a given position. So that's how we discriminate the position of the measurement. And analyzing this signal at this given time, we can retrieve informations of vibration, of temperature, and strain. And that's how it works. So we can have along tens of kilometers, even hundreds of kilometers, the equivalent of thousands of sensors or tens of thousands of sensors here on a simple standard optical fiber cable. And we're gonna do distributed acoustic sensing, that is what we call DAS, distributed temperature sensing, that we call DTS, can be Raman DTS, I will detail this further, and can be distributed strain sensing, DSS. So 3 measurements, 3 families of equipments we can deliver. The first I will detail is the G series. So it's for temperature and strain sensing. In fact, the technology is sensitive to both. So all our technologies, and as all our technologies, the G series equipments are single-ended. Means that you need to access only one end of a fiber optic cable to have a measurement. You don't need any loop. And nevertheless, the distance range is huge. With one single equipment, you can go further than 70 kilometers of range. So there are several versions of the G1 equipment. G1R is a classic rackable version, such as the equipment here on the right. G1C is a compact and autonomous equipment, such as here in the picture. G1D is an accelerated dynamic strain or temperature distributed sensing systems, and this operates in all single mode fibers. The second family is the FEBUS A series. So once again, it's single-ended, and then we're gonna measure acoustics. We're gonna measure vibration. And this, we're gonna do it with adaptable gauge lengths. I will detail this further in the presentation. We can address long distances with range of more than 50 kilometers and with very low noise floor. We talk to something about 3 picostrain per square root of Earth, which is the state of the art. It's compatible with any single mode fiber or any modern multimode fiber. Third family I will present today, it's Raman-based DTS, so distributed temperature sensing system. It is highly flexible, it's very cost effective. It has a mid-range capacities of 20 kilometers. It is operating on multimode fiber only, and this is the temperature sensing system clearly well suited for well applications. So that's why we're gonna see a lot of measurements coming from this instrument. And on the top of it, we have developed in-house repeater to reach longer distances. So with this equipment, we're going to extend the range of both G series and A series. I will detail this in a few slides. So with all those equipments, we can address several markets, from pipeline monitoring to infrastructure monitoring through geophysics applications, seismics in particular, I will detail a bit today, perimeter security, power cable monitoring onshore as well as offshore, and well monitoring. And that's this item I will detail today in my presentation. So to finish the corporate presentation, this is in yellow. You can see the different installations of FEBUS Optics equipments in the past. So you can see we are present and we can equip infrastructure worldwide. So next, I will go on presenting in further details the three technologies, so distributed acoustic sensing, distributed temperature sensing, and distributed strain sensing in great details. And then in the second part, I will give some case studies on well applications, for example, vertical seismic profiling, in-well monitoring, and DSS for well integrity applications. So first, and maybe the most popular equipment today, it's DAS, Distributed Acoustic Sensing System. So the name of our DAS is FEBUS A1R. So this is a summary of the data sheet of the A1R. So first of all, it's a phase-based measurement. In fact, there are two types of DAS technologies in the market. One is qualitative, gives you information you cannot quantify accurately, and the other one is quantitative. Here we are in the world of quantitative measurement, and that's why we can give a noise floor figure of 3 picostrain per root square of Earth. This is obtained with standard fibers. As I said before, and I will show you why it is important, we have the capability of changing the gauge lengths prior or after acquisition, meaning you have your data and then you can reprocess your data several ways to obtain several results with several gauge lengths. This is a unique feature from FEBUS Optics. We have a huge distance range. We can go down to 0.2 meter in terms of channel spacing. We can go higher frequency, up to 50 kilohertz, even on a 1 kilometer cable length. At low frequency, our equipment has been qualified, so we can give a figure at 10-3 hertz of 5 nanostrain, and I will show you a curve. Configuration is single-ended. We work on any fibers. No specific termination is required, meaning that we are not very sensitive to reflection. File format is an open format, HDF5, easily opened. You can easily open with many open software you can have access to. And the time stamping, which is very important, is very accurate. There is a GPS chip inside the box. So you have a microsecond precision time stamping. Data transfer can be done on several ports through USB, through standard Ethernet, or through high-speed network card. This can be very important because this type of equipment delivers a huge amount of data usually. And last thing, it is interoperable, meaning that through a socket, we can stream the data out of the box, giving access to the customer to the data real time, so the data can be processed with the own code of the customer, and then the customer can manage the data himself with his own protocol and save on his own volumes, for example. So as said before, this is the curve of qualification. So this is the noise curve. So you have picostrain per square root of Hertz as the y-axis as a function of frequency. It's a dB scale. And here you can see the noise floor, and you can see the noise floor increasing from 1 Hertz and below of 10 dB per decade. So here you can see we are able to measure with a high sensitivity even at 10⁻³ Hertz. I won't detail much this slide because it's very complicated and I have a lot of things to say after. But one thing which is very important is to have a huge dynamic range, meaning that the maximal amount of strain you can measure. And you know, with the A1R, we are at the theoretical limit. So here you have your maximum dynamic range, the maximum value you can reach, which is, let's say, which can be anticipated from theory, which is remarkable, actually. And this is, of course, depending on the parameters of acquisition. So we can easily reach 100 dB of dynamic range. Yeah, I will give you an example. An example is better than theory. So here, it's an experiment conducted on a cable. So here you have an image of the strain. So the y-axis here is the time. You have 4 seconds, and the x-axis is distance. And you have cross-section curves. Here you have the strain as a function of distance at 2 different times, one in blue, one in red. And here you have at one position the oscillation in terms of strain at one distance. And here you can see peak to peak, we are at 50 microstrain at 1 Hertz. If you remember, we were at something like 3 picostrain at this frequency. So it means something like between 7 and 8 order of magnitudes between what we measure and what we are able to measure. So this is the proof of a high dynamic range. So as said before, on the top of it, we can add this range extension module, REM, to extend the range much more than 50 kilometers, which is the nominal range. So you have the A1R, then you have your optical fiber cable, and then you can place this module. This module doesn't require any communication with the DAS. It requires only a small energy, 3 watts typically, can be powered by solar panel, for example, and it's composed of only very reliable components with the MTBF mean time before failure of about 25 years. So without maintenance, let's say. And then you extend your range, you double your range, and you put again 50 kilometers of cable, and then you have your signal. Here the signal is produced in the lab by a fiber stretcher, and then you can have your signal back at 100 kilometers instead of 50 kilometers as a standard. So, and then you can cascade several REM. You're losing a bit in terms of noise floor, but still you can recover your signal. You can go even further, and here it's more applied to subsea wells applications. So let's imagine you have a long umbilical length between an FPSO or a platform, and then you have a subsea well, and what the zone of interest is only the fiber which is located inside the well, downhole. So using this REM and using 2 fibers of the umbilicals here, we can overcome the limit of the fiber length to reach higher frequency even at further distance. We overcome the optical losses with the REM, and with this 2 fiber jump, we can overcome the limit of frequency, and then we have been able to measure at 50 kilometer signals up to 10 kilohertz. the limit would have been 2 kilohertz without this apparatus. Even more, you can use to enhance the backscattering and let's say increase the amount of signal coming back to the equipment. You can use engineered optical fibers in your zones of interest. So once again, you have your umbilicals or something which is not of interest for you, and you have your well which is of interest. So you will place this enhanced fiber here, and you will recover much more signal coming back from here. And then you can see here on this train curve, so you have the distance here with standard fiber at the beginning, and then enhanced fiber between 1 kilometer and 1.1. And you can see the noise floor is much lower in the enhanced fiber. And you can see here in the time domain and on the blue screen here on the frequency domain. At the end, you have a factor 6 on the noise floor, so you're improving of a factor 6 the noise floor in this case. Of course, in this case, we have simulated high losses to have the benefits of this enhanced fiber, which is much more efficient on far away from the equipment, or let's say with high losses. And then last but not least, you can combine enhanced fiber and range extension module to overcome lots of losses and a high range. So here you have 80 kilometer fiber and then an attenuation of 6 dB, representing something like wet mate connector, for example. And then you have your range extension module, and then you have your enhanced fiber. And then you can see here with this configuration, we can recover at 80 kilometer the same level of noise as at 0 kilometer in this case. So you can see the noise floor is varying from one slide to the other. It is due to the configuration. Actually, at 1 gauge length and 1 frequency of interrogation corresponds 1 noise floor. So, as I said, one of the unique features of FEBUS A1R is the tunability of the gauge lengths. You can do it either prior the acquisition, meaning your acquisition can be done with one gauge length or the other, or you can do it afterwards. And that's quite unique. So let's see how it behaves on an example. So this has been performed in Svelvik with Sintef. So they have this nice test site with 4 wells here, and they put a source in one well, which is the M1 well here, and then we measure the effect of the source acoustically in this well and on the other wells of the neighborhood. So here on the right, you have the image of let's say the acoustic image of those 4 wells successively. So the length of the fiber is on the y-axis and the time on the x-axis. Strain rate is given as a grayscale. And then you can see when we launch when we, let's say, activate the source in M1 well at time 0. So there is a lot of waves in the source well. And you can see here the first arrival on the neighbor wells. So you have M4 and M3 first, and then M2 well. And here you can see a very thin line corresponding to the first arrival. This is given at 2.4 meter of gauge length on stacked data. But let's see what happens if we increase the gauge length on the same data. So 1 acquisition and 4 results for 4 different gauge lengths in that case. So we move the gauge length from 2.4 on the left up to 8 meter on the right. And what you can see in the background is the noise floor is improving from left to right. Actually, you don't have those noise patterns anymore on the picture of the right, but the signal is disappearing as well. So here you have no gain in signal to noise ratio, and you're losing the signal. So you better use 2.5 meter gauge length. So that is the interest. If you don't know exactly what gauge length to use, you can move the gauge length and choose it and process your data. And you can even choose to process one span with one gauge length and the other span with the other, and so on. So that is one of the main features. So everything is configured and shown by our multitask user interface, which is called FOLOG. And it is let's say, really the key for use of the DAS. So you have this user interface allowing you to tune the measurement parameters, but you can do as well data processing and data visualization. You can tune the interoperability, so you can choose your storage. You can choose to stream out the data to a socket through an IP address. You can have access to the support from FEBUS Optics engineer with a remote support. And there is even a safe mode available to automatically restart the acquisition if something goes wrong. So just an overview of what the processing looks like in the screen when you open the guided user interface. So you have when the measurement is started, once it is started, you have this pipeline of processing here. You can tune, you can use filters provided by FEBUS Optics. You can even use pipelines provided by FEBUS Optics as a standard. And then you have those views here of signal in image or in line charts. There are standard charts provided, standard views provided by FEBUS Optics, but you can do your own view. And some of you may have recognized the ParaView interface, which is fully embedded with FOLOG software. So as a result, you can even just out of the box, you can produce this kind of image. So this has been produced directly on the box, FEBUS A1R with FOLOG. So you can do this kind of animation just with the standard software. And so it can provide you a nice image. So here it's a seismic shot, performed during an offshore seismic campaign. So from one platform to the other, and you have this shot here. You can see on the screen moving from top to bottom. So that was all for DAS. And now let's jump to T1R. So here I will be more brief on that one because it is a standard Raman DTS for well monitoring. So it will give you the information of temperature from top to bottom of the well on up to 20 kilometers. So it's enough for any well with a spatial resolution of 1 meter, sampling interval down to 0.2 meter, a repeatability below 0.1 meter, and that's the key. High stability and high repeatability to see very small events during well operations. We can produce equipment with up to 16 channel. It's always single-ended for multi-modes fibers, and the connections is standard industry connectors E2000 APC. Last technology, so Brillouin DSTS, so it's called DSS here because I will detail the strain part, but it's also able to measure temperature as well as strain. So the Brillouin based DSTS, spatial resolution down to 1 meter, meaning one sensor, the sensor size is 1 meter, sampling interval 0.1 meter, meaning the spacing between the center of the sensors is 0.1 meter. And the repeatability here is 2 microstrain. 2 microstrain meaning you expand the fiber over 1 meter of only 2 microns. It's very, very sensitive, much less than the DAS, by the way, but still very sensitive for static measurement. And depending on the application, the performances will vary if you explore more on the higher frequency and short distance or static mode on longer distance. So you can see here an example of dynamic mode. So at 100 Hertz, you will have a sensitivity of something like 50 microstrain at 2-meter spatial resolution over 500 meter and 100 hertz. On static mode, you can be much more accurate, even with 1 meter of spatial resolution. With a 10-second measurement at 1 kilometer, you can be at 8 microstrain, even 4 if you wait 1 minute with 2 meter of spatial resolution at 10 kilometer. So all the parameters are interdependent, but you can reach high frequency or high sensitivity in terms of strain. So it can be provided with 16 channel as well as the Raman DTS. And one unique feature is one channel can be dynamic, meaning at several tens of hertz up to 100, as seen before. And you can go even up to 4 channels dynamics on demand. It's always single-ended. It's using only single mode fiber. Some multi-mode fibers are compatible, but not all. So it has to be expertized if you want to do something like this. And the optical connectors are the same, E2000 APC. Here, a screenshot of the interface. So it's 4log G1. So it's not exactly the same type of data. But here you have something you can do, an example. You can just pin one point at one distance and show the evolution of the strain at that point together with the time. And you have the corresponding raw data here in the bottom. That can be done with 4log G1, but many more things and features are available, such as alerting, calibration, all the useful features for the field are provided. So, as stated before, one product over the family is compact and autonomous, meaning it's operating on battery. There is a battery here, and you have access to a charger here. And there is a touch screen, and it can act as a Wi-Fi hotspot. You have those antennas here, and then you can communicate with it even remotely. It can go at, let's say, middle speed, not 100 hertz, but few hertz, with 4 channels. And now there is a version you can use on outdoor, on rotary parts or moving parts. So this G1CX. So here the cap is closed, and you have access to the fiber here through those connectors. It's IP55, and then one of our customer is attaching the device to the reels, and he connects the cable he is deploying to the G1CX device, and then inside the truck he has a laptop, communicating with the G1CX and giving him the information on tension and bending of his cables. That's a very unique application. So on the top of all those technologies, and this will be the last slide on technology, pure technology. Afterwards, we will give you example. We have a monitoring software, which is called FOSA. So it's a versatile software. It can be used for any kind of visualization and alerts based on signal processed from all the technologies you have seen before. DTS, DSS, and DAS. So you have this waterfall view, meaning you have the history all over the distance of the thing you are measuring. Can be acoustic energy, can be temperature, can be strain, and then you can trigger alarms on it, and you can show the alarms on a map, or you can transfer the alarm through Modbus or through other protocols to any SCADA or VMS. So now let's jump to the application part of the presentation. So it's dedicated to well applications, and we're gonna see how those technologies fit on this well application. First, I'm gonna give an example of seismic, vertical seismic profiling acquisition. Then we will see in-well measurements using DTS and DAS, and then we will see how we can do well integrity monitoring using DAS and DTS and DSS. Sorry. So first of all, if you want to measure something in a well, you have to install a fiber optic cable in a well, because that's the goal, is to measure something in the well. So 3 types of deployments are basically possible. One is the permanent deployment, and in this case, the fiber optic cable will be behind the casing and cemented. Another one is called semi-permanent. So the cable will go down here with the tube, the completion tube here, the production tubing, and then it's clamped here at the descent of this tube. And third is the temporary deployment. So you can use different apparatus to do that. Simple wireline, fiber optic cable in a wireline, or just a wireline made of fiber optics. So here you have an example of deployment we have done, or what we call here fish. In fact, here is a FLI system from WellSense, and this the fiber here is into the torpedo, and the fiber is deploying itself. It's self-deploying when the torpedo goes down, and then you connect to the head here, and you have your measurement from top to bottom. So knowing that, an example of vertical seismic profiling. So what is vertical seismic profiling? I will give a basic explanation of it. So you have the fibers, the fiber which is deployed into the well permanently, semi-permanently, or temporarily, just as we saw before. And then we connect this fiber to a distributed acoustic sensing system. And then with a truck, we're going to vibe the ground here. It's called a vibrosize. So we're going to vibe the soil with a sweep signal. And then the signal will reach here, the fiber, at different times, giving the opportunity to have an image of the underground. So this is the kind of signal we can extract directly from the DAS. So you have the depth here in the y-axis, the time in the x-axis, sorry. And then when you correlate the signal to recover the pulse response, and you stack to enhance here the signal to noise, you have this kind of signal. And then you can do offsets, moving the source at several points and moving away from the wellhead to a faraway location. So here, an example of experiment we have performed and conducted with partners, WellSense, KM1, Real-Time Seismic, P2LS, and GTG in the southeast of France. So it was a 1,080 meter deep well, and we moved the source from offset 0 here to offset 4 here, and give shots at those several points. We use several deployments, the fish I mentioned before, the wireline, and we take this opportunity to insert between the instrument, which was the A1, which was in the truck, between this instrument and the well, we insert a surface cable. You see here the coupling is done by small stones. Let's say it's a rough coupling. We will see the results, and different sources, block folds, and vibrosize. So here you have an example of the results. So this is the seismic image, and this is the completion diagram. You can see the different layers of the completions and different elements of casing, and you can see a certain match between those elements and some kind of discontinuities. You can see horizontal discontinuities you can see in the image. That's the first. So this is because we have taken a lot of care of the depth control. In this, one of the major calibration you have to do when you do such an operation is to control very accurately the depths, knowing the 0 is here, and here is the bottom of the well, and we are exactly at 1,907 meters away from the top of the well. And then here on the image, we can have a look at several particular wave fronts. So the downgoing P wave front, and you can see some upgoing waves here. On the top here, we see only casing ringing with the noise actually, which is not seismic. It's a ringing, pure ringing. We can see S waves here in black with black arrows, and a lot of tube waves, which are due to waves guided by the casing here. So it's not seismic as well. So this result is obtained with the wireline cable, adding a lot of slack to the cable to enhance the coupling. Now, if we move to the same experiment, but with the fish, so the FLI, so it's we have much more effect from tube waves. Results are consistent, meaning the first arrival, if we plot the first arrival from the previous wireline measurement on this diagram, we see a match. But in this case, it's not in general, but in this case, one deployment was much more practical than the others, especially for smaller offsets. And then when you have your DAS acquisition signal, so you can go to processing. So real-time seismic here was in charge of the processing. So they can do the processing and they can image the underground with the data. So as I said, we took this opportunity to make some surface measurements. So we coupled with small stones, so very roughly the cable on the soil, and we compared this DAS acquisition with standard strides nodes here. So here you have the route of the nodes in yellow and the route parallel of fiber optics, and then it's just preliminary results, sorry. But you can see the signal coming from stride nodes and the raw signal coming from A1R and fiber optic cable. And you can see that in terms of signal to noise, the A1R is not too bad, even if the fiber is not well coupled. So you have some resonances here, you can see, due to this bad coupling. But processing is ongoing, and we expect to have a good result and a good match when we will take care of units of both measurements here. So second application is INWA monitoring. So here we're going to use DTS and DAS, and we will track an interface during a well operation. So here the level of liquid in the well is increasing from bottom to top. And what you can see here is a DTS image. So here you have the depth in y-axis. You have the time, which is in minutes. So it's quite slow process. And you have a temperature front here moving from bottom to top because the liquid level is increasing. And we have some kind of, let's say, a cloudy zone here where we don't know if it is liquid or gas. So if we differentiate this temperature data, trace by trace, trace to trace, sorry, we have this kind of pattern. And here we can differentiate two clear zones and one mixing zone here in the middle. But we are not able to detect this very early. If we use DAS in the meantime, at very early stage, much earlier, we can see this interface here moving from top to bottom, and then it is a perfect continuity of this noise measured by DAS of this interface with the temperature front measured by the DTS. So this has been made in the meantime with the same cable, two different fibers, one using DTS continuously and one using DAS continuously as well, and it's a remarkable example of complementarity of the two techniques. With the DTS as well, you can measure temperature, as we have shown before, but you can do relative temperature measurement from a baseline and stimulate something to see something more accurately. Here, the aim was to see the perforation efficiency. So they stimulated them, injecting water, and then when stopping the injection, you can see temperature increase due to production of the perforations. So that's what you did. So you can see here the zone of production. Another thing you can do with the same apparatus is trying to detect leaks. For example, if you have a leak on your production tubing or on the packer, if there is one, and it was the case here. So you will have this type of diagram. So here, the signal is plotted in the frequency domain. So you have here the depth on y-axis, the frequency on x-axis, and in color, you have the intensity of the signal. So you can see the majority of the signal all along the tube, it's at low frequency due to activity in the well, due to fluid movements. But at the bottom of the well, here at a given location, and very you can easily distinguish this location, you have a higher frequency signal, which is due to a leak actually. And it's clearly at high frequency. Here you have three signals, one at lower frequency, one at middle frequency, and one at higher frequency. And you can see clearly the leak at higher frequency. So that's how we can detect the leak directly using FEBUS A1R and this small interface. Finally, I will show you a well integrity application measuring strain on the casing. So first, if you want to measure strain on the casing, the best way of doing it is to attach the fiber to the casing first. So that's quite obvious, but the cable has to be quite particular and it should be tight buffered. Why? Because otherwise, if the cable is not tight buffered, the optical fiber will slip on the tube inside the cable, and then it will decrease the sensitivity. On the diagram on the right, you can see tight buffer fiber response to strain in blue, black, and red solid curve compared to, at same location, loose tube fiber. So you can see a decrease of the sensitivity and something like a non-repeatable and non-consistent behavior. So that's at first. And then if you want to differentiate tension from bending, for example, you will need several fibers on the cross section, or one fiber coiled with an angle here around the tube. Actually, it's very difficult to do that in practice at high depth. So usually several fibers can be deployed. So, and then from those fibers, you can have the information on the shape or on the displacement of the casing. So with this small experiment we have done in our test center, I will show you how it works. So the experiment is quite simple. You have this casing here, and this casing is equipped, as on the top right here, by 4 optical fiber cables. And one, they are at 90 degrees with respect to their neighbors. And one is on the top, one is on the bottom to monitor the bending we will produce, and one on the left and one on the right to monitor the transverse bending. And then we're going to lift the casing by its middle with the overhead crane, and then the casing will bend with the effect of its own weight. So we have this equation between the vertical displacement and the strain we are measuring. So by double integration, we're going to calculate the displacement and we're going to control and compare, sorry, the calculation with the actual value we can measure with this small arrow here in the field. So here is the experiment. So I will launch the video, but first a brief presentation of the interface. So the device was connected to the fiber for strain measurement, and we have this small application done by a third-party computer. So we gather this application with the data from the device, and then we do our own calculation and show here strain on the 4 fibers. Here, longitudinal, transverse, and bending strain here. And here, the same, but just at the point of the center. And here in the bottom, that's the interesting part. We're gonna reproduce by double integration the casing shape here in that diagram. And here, we're gonna monitor the casing location in that quadrant here. We're gonna locate the casing position at the at the center here, meaning in the middle of the casing. So let's go. So here you can see we're gonna lift the casing up as it's stated here, and you can see the strain is increasing on the top, decreasing on the bottom, creating here a bending strain in Z. We have this 10 centimeter of displacement here, and you can see the same here. We're gonna to red, from red to red, which is 10 centimeter, and we can follow accurately on the interface real time the position of the casing. So it means that that is really working. So you can measure the shape from the strain using distributed strain sensing. Just the boundary conditions have to be strictly fixed. For example, for a well, you will say the bottom of the well is at the fixed position and fixed inclination, or on the contrary, the top, depending on your application. And then you will integrate your equation. So for this strain monitoring, as you may have been surprised, because we spoke about strain for DAS and strain for DSS. It's the same strain actually, but it's not the same time scale. With DAS, we will measure strain, but short term. For example, if we want to do frac monitoring, we will use DAS to have a huge sensitivity in slow strain, but slow means minutes or hours, one day, let's say, but not years. With Brilliant DSS, you have no drift, so you can measure over years. And this can be done to do structural health monitoring of the casing during the lifetime. You can monitor even the shape and see some shears or some subsidence. You can monitor, relatively short term for cementation, for example, but you can follow the cementation long term as well. That's the end of my talk. Thank you very much for your attention. And now I'm open for question. And if you want to contact me afterwards, you can use this email address on the screen.
Thank you very much, Vincent, for a very informative presentation. We have time for a few questions. One, you obviously have showed the interface with the waterfall, the sort of visualization of the what the technology picks up. In implementation, do you recommend relying on that, or do you use software alerts to sort of streamline the interpretation process?
Actually, there are different possibilities. For basic processing, you can do everything from the box and then save the process data, even if you want directly on the storage. If you have your own codes, and if you want to use your own code because you have your own processing and you know your processing is working fine, operating very nicely on your machine, so you will stream out the data and then gather your model or your processing with our data and then do your own computation. But at the end, you can even do your processing, and then go back to the forward alerted software. It's something we have already done. So you have the acquisition, and then you have the processing, and then you have the alerting. And the processing in between can be done by a third party without any problem. So many possibilities, I would say.
So I think that then is related to the next question, which is that when you mean static mode, does that mean that the data is collected and processed online? So that is, I guess that's what you're describing then.
Yes, yes. When I say static, it's just about long-term or short-term, but it can be done without saving. It's not a problem of collecting the data. It can be done through file or through sockets. Even if it's slow, that's not a problem to do it through sockets. It's more secure to do it from files if it is static. But yeah, that's not the problem. Yeah, both can be done.
Got it. In liquid level monitoring, do you convert the DAS waterfall into absolute temperature units? Did you account for strain there?
No, on the liquid level monitoring, what I showed was just acoustic energy in a frequency band, dedicated frequency band. It was not linked to slow strain. It was not at 0 frequency. It was at something like 5 to 100 hertz frequency, integration of energy over this energy band.
And another interpretation question for the DAS system, do you have features that can differentiate different types of vibration source? So, for example, human walking, car driving, pipe leaking?
Yeah, this is something I didn't evoke during my presentation, but we have machine learning processing. So we have specialists in-house at FEBUS Optics of that kind of models. So to do automatic classifications of events, we do this very frequently for pipeline monitoring, for example. When you want to discriminate vehicles from excavators, from pipeline leaks, from normal industrial activities, for example. So we have this machine learning model. But one more time, it's in between. You have the data from the DAS, we collect them, it's gathering the model, and then the model gives the answer of what's the class of the event. And then this goes to the alerting system, and the alerting system will say it's a human walking over the pipeline, or it's an excavator. But the model is in between. You have the acquisition, the model or the processing, and then the alerting. But the alerting is capable of indicating different classes, of course, or different level of alerts, or yeah, anything. It's very versatile.
So it wouldn't be a FOSA webinar if we didn't get a question about the kind of cable you were using. So for VSB testing within loosely coupled surface cable, are you using standard cable or enhanced fiber?
It was standard fiber. The fiber was not enhanced or engineered, but the cable was tight buffered, meaning the fiber was well coupled to the cable, inside the cable. And that's why the results are so good, actually, because the coupling is actually quite good, because the coupling of the fiber into the cable matters. Not only the cable with the ground or the soil, but the coupling between the fiber and the cable, inside the cable, this matters, actually. And this was optimized.
So we have time for one more question, but I do say you captured the interest with discussing the length, maximum distance for beryllium measurements. So again, was that single mode fiber, or were you using enhanced fibers, a different standard of cable?
I'm not sure I understand.
I'm sorry, when you were extending the distance for your measurements.
Yes, it's standard fibers. At the end, you can put an enhanced fiber if you want even more enhancement. I mean, actually the range extension module, it's a kind of enhancement between you're repeating the signal, let's say. So that's one kind of increasing the level of signal. Another way of increasing the level of signal is using an enhanced fiber. So I showed 3 examples. One was range extension module alone. Another one was enhanced fiber alone. And another one was both. And it was for DAS. But for Briouin, we cannot use enhanced fiber. It's only standard fiber. So we use the range extension module alone for long range DTS or long range DSS.
Well, thank you very much. We've come to the top of the hour and we do cut things off, but your contact information is available for people with additional questions. And for those who want to listen again or share the presentation with colleagues, which we certainly recommend, within a matter of hours, we will be adding this to our library, FOSA library of presentations on our YouTube channel. Vincent, thank you very much. And that concludes this webinar.
Thank you very much.